The light comes first to the highest peaks, touching them with gold while the valleys below remain wrapped in darkness. This is how it has always been, the summits standing so far above the earth that they intercept the sun's rays long before the light reaches those who dwell at lower elevations. The peaks glow, luminous against the deep blue of the pre-dawn sky, seeming to float, disconnected from the earth, suspended in that liminal space between night and day, between earth and heaven. You stand in the cold air, your breath visible in the thin atmosphere, watching this transformation, this daily miracle of light descending from the highest points downward, illuminating ridge after ridge, revealing the immense architecture of stone that rises before you. These are the Himalayas, the roof of the world, the highest mountains on Earth, home to all 14 of the planet's peaks that exceed 8,000 meters, including Everest, Sagarmatha, Chomolungma, the mountain of many names that rises higher than any other point on the planet's surface. The scale is difficult to comprehend. Your mind struggles to process the vertical distance, the sheer mass of rock piled impossibly high. These mountains rise more than 5 miles into the sky, their bases rooted in the foothills, their summits piercing the upper atmosphere where the air is so thin that human life cannot be sustained without artificial oxygen. The mountains stretch for 1,500 miles, a continuous wall separating the Indian subcontinent from the Tibetan plateau, creating a barrier so formidable that it shapes the climate of half of Asia, influences the monsoons that water billions of people, determines the course of rivers that are sacred to ancient civilizations. But the most remarkable thing about the Himalayas, the fact that makes them unique among Earth's mountain ranges, is not their height, or their extent, or their cultural significance. It is this: they are still growing. Right now, as you stand watching the light descend from peak to valley, these mountains are rising, pushing upward, gaining elevation. The process is slow, measured in millimeters per year, imperceptible on human timescales, invisible to anyone watching in real time, but it is happening, has been happening for 50 million years, and will continue to happen for millions more. This is silent growth, the kind of change that occurs too slowly to see, but too powerfully to stop. It is the result of two continental plates colliding, the Indian plate driving northward into the Eurasian plate, the impact crumpling and thickening the crust, forcing it upward, creating these mountains through the application of unimaginable force over unimaginable time. Every year, India moves about 2 inches closer to Asia, and every year the mountains respond, rising, buckling, adjusting to the continued compression. The growth is not uniform. Some peaks rise faster than others, some areas are uplifting while others are being pushed sideways or even downward. The system is complex, the forces acting on it distributed unevenly, the response of the rock varying depending on its composition, its temperature, its history. But the overall trend is clear. The Himalayas are rising, have been rising since the moment of initial collision, and show no sign of stopping. This ongoing growth is counterbalanced by erosion. The mountains are not just rising, they are also being worn away, attacked constantly by water and ice and gravity. The monsoon rains that fall on the southern slopes are among the heaviest on Earth, delivering water that cuts into the rock, that carries sediment away, that reduces the mountains grain by grain. The glaciers that mantle the higher elevations carve valleys, pluck rock from the walls, grind stone to powder. Landslides and avalanches move vast quantities of material downslope, transporting it toward the rivers that will ultimately carry it to the sea. The race between uplift and erosion determines the height and form of the mountains. If uplift were to stop, erosion would gradually reduce the Himalayas, wearing them down over millions of years until they were low hills, mere remnants of their former grandeur. But as long as the collision continues, as long as India keeps pushing northward, the uplift will continue, replacing what erosion removes, maintaining the mountain's height, ensuring that the roof of the world remains aloft. This is the story we will explore, the story of mountains that rise while we watch, though we cannot see them rising, that grow in silence, that are both ancient and still forming, that represent both permanence and change. It is a story told in stone, written in the layers of rock that make up these peaks, recorded in the fossils that can be found at impossible elevations, preserved in the glacial valleys and river gorges that dissect the range. It is a story that spans 50 million years and continues into a future we can only imagine. A story of collision and compression, of uplift and erosion, of rock and time and the forces that shape our planet. The light has reached the valley now, illuminating the terraced fields and the scattered villages, the prayer flags fluttering in the morning breeze, the trails that wind upward toward the higher passes and the peaks beyond. The mountains stand revealed, massive and complex, ridge after ridge receding into the distance, snow and rock and ice glowing in the early sun. This is the view that has drawn humans to these heights for thousands of years, that has inspired religions and philosophies, that has tested the limits of human endurance and ambition. But beneath the beauty, beneath the cultural and spiritual significance, beneath the challenge they present to those who would climb them, the mountains are engaged in their own drama, operating on timescales that dwarf human history, responding to forces that have nothing to do with our presence or our perceptions. The Himalayas are a geological phenomenon, an ongoing expression of plate tectonics, a natural experiment in what happens when continents collide. To understand them fully, you must look beyond what your eyes show you, must learn to see the processes that are hidden, that occur too slowly to observe directly, that reveal themselves only through careful study and patient observation. As you begin to walk, following a trail that leads upward toward the higher elevations, you are walking into deep time, into a landscape where the present is just one moment in a story that began 50 million years ago and will continue for 50 million more. Every step takes you higher, closer to the peaks, deeper into the architecture of stone that records this ongoing collision. The trail is steep, the air growing thinner, the temperature dropping as you ascend. But the effort is worthwhile, because understanding the Himalayas requires more than viewing them from a distance. It requires entering them, experiencing their scale, feeling the rock beneath your hands, seeing the layers and structures that reveal their history.
The story of the Himalayas is the story of India's journey from the southern supercontinent of Gondwana, a journey that began more than 100 million years ago when the landmass that would become the Indian subcontinent broke away and began its northward migration across what was then the Tethys Sea. It is the story of an ocean that closed, of seafloor that was consumed, of the moment when two continents finally met and the collision began. It is the story of what happens when irresistible force meets immovable object, when neither can yield, when the only resolution is to go up, to buckle and fold and thrust the crust skyward, creating mountains where once there was ocean. And it is a story that is still being written. The collision continues, the mountains rise, the erosion wears away, the balance shifts and adjusts but never reaches equilibrium. The Himalayas are a work in progress, an unfinished creation, a landscape in transition. They are not what they were 50 million years ago. They are not what they will be 50 million from now. They are what they are in this moment, this geologically brief instant that we happen to inhabit, and they will continue to change, to evolve, to respond to the forces acting upon them long after our species has disappeared and been replaced by whatever comes next. This is humbling, this perspective of deep time, this recognition that we are witnesses to a process that began before we existed and will continue after we are gone. But it is also inspiring, because it shows us that the Earth is alive in a way we often forget, that our planet is not a static stage on which life plays out, but an active participant constantly reshaping itself, constantly creating new landscapes and destroying old ones, constantly demonstrating that change is the only constant, that nothing remains the same, that even mountains, those symbols of permanence and stability, are temporary features, products of forces that will eventually cease or change, leaving behind only the eroded remnants and the geological record of their existence. As the morning advances and the sun climbs higher, warming the air, melting the overnight frost, you continue your ascent, following the trail as it switchbacks up the mountainside, gaining elevation with each turn, each step. The view expands with height, revealing more peaks, more valleys, more of the vast landscape that constitutes the Himalayas. And with each gain in elevation, you move upward through time, through the layers of rock that were deposited as sediments millions of years ago, that were then buried and compressed and heated and uplifted, that now stand revealed as the solid stone of these mountains. The Himalayas are not just mountains. They are a library, a record, an archive. They contain within them the history of their own formation, the story of the collision that created them, the evidence of the forces that continue to shape them. To read this record requires knowledge, requires understanding geology and the principles that govern how rocks form and deform and reveal their secrets. But even without formal training, even as a casual observer, you can sense the story, can feel the age and the power, can intuit that these mountains are more than they appear, that they contain depths of time and meaning that reward careful attention and patient study. This is the journey we will take together, a journey through the Himalayas, not just as a physical space, but as a geological phenomenon, as a window into Earth's processes, as a testament to the power of slow, persistent forces operating over vast spans of time. We will explore how these mountains formed, why they continue to rise, what forces balance growth and erosion, how life adapts to extreme elevation, what the future holds for the roof of the world. And we will reflect on what these mountains teach us about time, about change, about our place in a universe where human history is but a brief moment, a flicker, a single heartbeat in a story that began billions of years ago and will continue for billions more. The trail leads onward, upward, into the heights. The peaks stand silent above, growing imperceptibly, their silence not the silence of stillness, but the silence of processes too slow for human perception, too vast for easy comprehension. The Himalayas are speaking, but in a language of millimeters and millennia, of uplift and erosion, of rock and time. To hear them requires patience, attention, a willingness to think beyond the human scale, to embrace the perspective of deep time. And that is what we will do, here, now, as we begin our exploration of the silent growth of the roof of the world.
The Kathmandu Valley sits at an elevation of about 6,400 feet, cradled between hills ringed by mountains that rise on all sides. The valley is a green bowl, fertile and populous, home to millions of people, scattered with temples and stupas and the remnants of ancient kingdoms. But the valley's true significance, the reason it exists at all, is geological. This was once a lake filled with water, surrounded by mountains. Over thousands of years, the lake drained as its outlet gorge was cut deeper by the river, leaving behind the flat valley floor of sediments that make the soil rich and the farming productive. From certain places in the Kathmandu Valley, on days when the air is clear, you can see them. The high Himalayas, rising to the north, a wall of white peaks stark against the blue sky. The view is startling in its abruptness, in the way the mountains seem to leap upward from the middle hills, gaining thousands of meters of elevation in just a few horizontal miles.
This is the consequence of the collision, the result of compression that has not just lifted the crust, but has also thrust it, creating zones where younger rock rides up and over older rock, where the vertical rise is steep and dramatic. Standing at the edge of the Kathmandu Valley, looking north toward these peaks, you are looking at some of the youngest and most actively rising mountains on Earth. The view encompasses a vertical distance of more than 20,000 feet from where you stand to the summits visible in the distance. This is more than 4 miles of elevation gained, a rise so dramatic that it affects the climate, creating barriers to airflow, forcing the monsoon moisture to rise and cool and drop its water on the southern slopes, leaving the northern slopes in the rain shadow much drier. The peaks you see from Kathmandu are not the highest. Those lie farther north and west, in more remote regions, but they are impressive nonetheless. Langtang Lirung, Ganesh Himal, Dorje Lakpa, names that mean something to those who live here, who see these mountains as sacred, as homes of gods, as places where the earthly and divine intersect. For the local people, these mountains are not just geological features, but are imbued with spiritual significance, are part of cosmologies that stretch back thousands of years, are woven into the fabric of culture and religion and daily life. The cultural relationship between humans and the Himalayas is ancient and complex. For Hindus, the mountains are the abode of Shiva, destroyer and transformer, who meditates on Mount Kailash. For Buddhists, the mountains are sacred spaces, places of pilgrimage, locations where monasteries perch on impossible ledges, where monks seek enlightenment in the thin, cold air. The Sherpa and other mountain peoples have their own traditions, their own stories about the peaks, their own relationships with the heights that combine practical knowledge of survival at altitude with spiritual respect for the power and danger of the mountains. This human dimension is important, is part of the Himalayan story. These mountains are not empty wildernesses, not uninhabited peaks. They are home to millions of people, are the source of water for billions more, are the setting for some of humanity's most profound spiritual and philosophical traditions. Any understanding of the Himalayas that ignores the human presence is incomplete, is missing a crucial dimension of what these mountains mean, how they function, why they matter. But for now, we focus on the geology, on the physical processes that created and continue to shape these peaks. The view from Kathmandu provides an entry point, a perspective from which to begin understanding the scale and structure of the range. The mountains you see are the southern edge of a much larger system, the beginning of a belt of high peaks that extends for more than 1,000 miles, curving from Pakistan through India, Nepal, and Bhutan before turning south into Myanmar. This is the Himalayan arc, shaped by the geometry of the collision between India and Asia, following the line where the two plates meet and continue to contest each other. The shape of this arc is not random, but reflects the three-dimensional geometry of the collision. India is not colliding with Asia along a straight line, but is pushing into it like a fist into clay, creating a curved zone of deformation. The western and eastern ends of the arc, the so-called syntaxes, are regions of particularly complex deformation, where the collision zone bends sharply, where multiple forces interact, where some of the most dramatic uplift and erosion occur. Understanding this three-dimensional geometry is crucial to understanding why the Himalayas look the way they do, why the peaks are distributed as they are, why certain areas rise faster than others. From Kathmandu, the mountains appear as a two-dimensional backdrop, a wall of peaks lined up along the northern horizon. But this is an illusion of perspective. The reality is a thick belt of mountains, dozens of miles from north to south, containing multiple parallel ranges separated by valleys, cut by rivers, rising in stages from the lowlands of the Terai through the middle hills to the high peaks, and finally to the Tibetan plateau beyond. This complexity is not visible from a single viewpoint, but reveals itself only to those who venture into the mountains, who cross from south to north, who experience the multiple zones that make up the Himalayan system.
The geology of what you see from Kathmandu is complex, the product of 50 million years of compression, uplift, and erosion. The rocks that make up these peaks were once sediments on the floor of the Tethys Sea, the ocean that separated India and Asia before the collision. As India approached, the seafloor sediments were scraped off the descending Indian plate and accreted to the southern edge of Asia, a process that continues today. These sediments were buried, heated, compressed, metamorphized, transformed from soft muds and sands into hard rocks capable of supporting mountains. They were then thrust upward along great faults, lifted into the air, carved by rivers and glaciers into the peaks we see today.
This process, sedimentation, burial, metamorphism, uplift, erosion, is the fundamental cycle that creates mountains. It operates everywhere that tectonic forces drive plates together, everywhere that compression occurs. But in the Himalayas, the process is particularly vigorous, particularly rapid, because the collision between India and Asia is ongoing and forceful. The Indian plate is not just pushing against Asia, it is attempting to subduct beneath it, to dive down into the mantle. But because continental crust is buoyant, less dense than the mantle, it resists subduction. The result is a pileup, a thickening of the crust, a forcing upward that creates the high elevations we see. The rate of this uplift varies across the range and changes over time. But GPS measurements show that some areas are rising at rates of several millimeters per year, sometimes as much as 10 millimeters in particularly active zones. This might not sound like much. 10 millimeters is less than half an inch, but sustained over geological time, over millions of years, it adds up to thousands of meters of uplift. The Himalayas are perhaps 25,000 to 30,000 feet high on average in the high peaks region, which means that if uplift has been occurring at current rates for the entire 50 million years since collision began, the cumulative uplift would be much greater than the current elevation. This tells us that erosion has been removing material as fast or faster than uplift has been adding it, that the current height represents an equilibrium, a balance between building and wearing away. This balance is dynamic, not static. It shifts over time as climate changes, as the monsoon strengthens or weakens, as glaciation advances or retreats, as the rate of plate motion varies. The mountains respond to these changes, adjusting their form, their height, their profile. In some periods, uplift dominates and the mountains grow higher. In others, erosion dominates and the mountains are cut down. The current configuration, with peaks exceeding 8,000 meters, may not be the highest the Himalayas have ever been, nor is it necessarily the highest they will become. The mountains have a history of varying elevations, and their future height will depend on factors we cannot fully predict. Looking at the mountains from Kathmandu, you see the result of this ongoing process, this competition between uplift and erosion. The peaks are sharp, rugged, heavily dissected by valleys, showing the signature of vigorous erosion. The slopes are steep, often near the angle of repose, the maximum angle that loose rock can sustain before gravity causes failure and landslides occur. The rivers cutting through the mountains have carved deep gorges, some of them thousands of feet deep, evidence of the power of flowing water to cut through rock given enough time. But you also see evidence of uplift, of the mountains rising. The peaks themselves, standing higher than any surrounding land, are testimony to vertical motion. The thrust faults visible in some cliff faces, where one layer of rock has been pushed up and over another, show the compressional forces at work. The folded rock layers, bent and contorted, reveal the plasticity of rock under pressure and heat, the way even solid stone can flow when subjected to sufficient force over sufficient time. The view from Kathmandu is thus a lesson in geology, a textbook open to the chapter on mountain building, with examples visible on a scale that makes them impossible to ignore. Every peak, every ridge, every valley tells part of the story of collision and uplift and erosion.
The mountains are not a finished product, but a work in progress, a landscape caught in the middle of its evolution, neither fully formed nor finished with its transformation. They are what they are in this moment because of the specific balance of forces acting upon them right now, and they will be something different in the future when that balance shifts, as it inevitably will. As the day advances and the light changes, the mountains change with it. Shadows shift, highlights move, colors intensify or fade. The peaks seem to breathe, to live, though the changes you observe are merely the play of light on static stone. But in a deeper sense, the mountains are alive, are active, are engaged in processes that constitute a kind of life, a dynamism that exists at timescales too slow for human perception, but is real nonetheless. The growth of mountains, the rise of peaks, the building of the roof of the world, this is a form of geological life, a planetary metabolism, Earth's ongoing creation of new topography, new landscapes, new environments. Watching the mountains from the valley, you become aware of your own smallness, your own brevity. You stand here for a moment, a fraction of a second in geological terms, observing peaks that have stood for millions of years and will stand for millions more. Your lifespan, your entire species' history is infinitesimal compared to the timescales on which these mountains operate. And yet you are part of the same universe, subject to the same physical laws, made of the same materials. The atoms in your body were forged in stars and will outlast you by billions of years, moving through cycles of formation and destruction, becoming parts of other structures, other beings, other worlds. This perspective, this recognition of deep time and human transience, is part of what the Himalayas offer to those who contemplate them. The mountains are beautiful, yes, but their beauty is enhanced by understanding, by knowing something of their history and their ongoing evolution, by recognizing that what seems permanent is actually temporary, that what appears static is actually dynamic, that silence can conceal profound activity. The Himalayas are growing, silently, patiently, inexorably, and we are here, briefly, to witness them in this particular moment of their long existence, to marvel at their height, to study their formation, to learn what they can teach us about our planet and ourselves.
To understand how the Himalayas came to exist, you must travel backward in time, must envision a world profoundly different from the one we inhabit, a world where the continents were arranged differently, where oceans existed that have since vanished, where the Indian subcontinent was not attached to Asia, but was a separate landmass drifting slowly northward across what was then the Tethys Sea. This journey backward takes us more than 100 million years to the Cretaceous period, the age of dinosaurs, when the supercontinent of Gondwana was breaking apart. Gondwana, that southern supercontinent that once included South America, Africa, Antarctica, Australia, and India, began fragmenting around 180 million years ago. The breakup was driven by mantle plumes, upwellings of hot rock from deep within the Earth that pushed against the overlying crust, stretching it, thinning it, eventually rifting it apart. One by one, the pieces separated, creating new ocean basins between them, establishing the pattern of continents we recognize today. India was one of the last to break away, finally separating from Madagascar and Antarctica around 90 to 80 million years ago. Once separated, India began its remarkable journey northward. The landmass was carried along by the motion of the tectonic plate on which it rode, moving at rates that were unusually fast by plate tectonic standards, perhaps as much as 6 inches per year during certain periods. This is rapid movement for a continent, and it meant that India covered the distance from its starting position near Antarctica to its eventual collision with Asia in a geologically brief span of about 40 to 50 million years. As India moved north, it crossed the Tethys Sea, a vast ocean that separated Gondwana-derived continents from Eurasia. The Tethys was an ancient ocean older than India's journey, a body of water that had existed in various forms for hundreds of millions of years. The seafloor of the Tethys was being created at a spreading ridge to the south of India and was being consumed at a subduction zone along the southern margin of Asia to the north. India's northward motion was driven by this subduction process, the seafloor being pulled down into the mantle, dragging the continent behind it. The Tethys Sea was not empty. Like all oceans, it supported life, including abundant marine organisms that built shells and skeletons from calcium carbonate extracted from seawater. These organisms, mollusks, corals, foraminifera, and many others, lived and died, their hard parts accumulating on the seafloor as sediments. Layer upon layer of these biological remains, mixed with sediments eroded from the continents and carried to the sea by rivers, built up on the Tethys seafloor, creating sequences of limestone and shale that would eventually become part of the Himalayas. This is one of the most remarkable aspects of the Himalayan story. The rocks that now form the highest peaks on Earth, including Mount Everest, were once sediments on the floor of an ocean. The limestone found near Everest's summit contains fossils of crinoids and other marine organisms that lived in the Tethys Sea. To stand on Everest's summit is to stand on what was once seafloor, lifted nearly 6 miles into the air by the collision of continents, transformed from horizontal layers of soft sediment into tilted, fractured, metamorphosed rock forming the top of the world. As India approached Asia, the distance between them narrowed. The Tethys seafloor continued to be consumed by subduction, sliding beneath the southern edge of Asia and descending into the mantle. The ocean became progressively smaller, its northern and southern margins drawing closer together, and then, about 50 million years ago, the ocean closed entirely. India made contact with Asia, and the collision began. The exact timing of this initial contact is debated among geologists. Different lines of evidence suggest dates ranging from about 55 to 45 million years ago. The uncertainty reflects the complexity of defining what collision means when continents come together. The process is not instantaneous but gradual, with initial contact occurring in some areas while ocean remains in others, with the geometry of collision changing as the continents continue to converge and rotate. But by about 50 million years ago, the collision was well underway, and the Himalayas were beginning to form. When continents collide, unlike when oceanic plates collide, neither can easily subduct. Continental crust is too buoyant, too light compared to the underlying mantle to sink readily. The result is that the crust crumples, folds, pile up on each other. This is analogous to what happens when continents collide, though the forces involved are millions of times greater and the materials are solid rock rather than foam. The compression created by India's continued northward push deforms the crust in multiple ways. Rocks fold, bending into anticlines and synclines, creating wave-like patterns of ups and downs. Faults form, fractures along which rock masses slide past each other, with some blocks moving up and others moving down. The most important faults in the Himalayas are thrust faults, where older rock is pushed up and over younger rock, creating stacks of rock layers that greatly thicken the crust.
The main Himalayan thrust, or MHT, is the primary fault along which the Indian plate is being pushed beneath the Himalayan mountain range. This is not a single discrete fracture, but rather a zone of deformation that extends tens of miles underground. Along this zone, the Indian plate continues to move northward, sliding beneath the mountains at rates of about 2 inches per year. The friction and resistance encountered as the plate moves generates earthquakes, some of them very large, that are the growing pains of these young mountains. The collision also generates heat. The compression and movement of rock creates friction, and friction creates heat. Additionally, as crustal rocks are buried deeper and deeper by the thickening crust, they are subjected to higher temperatures from the Earth's internal heat. These elevated temperatures cause metamorphism, the transformation of rock from one type to another through heat and pressure without melting. The sedimentary rocks that were deposited on the Tethys Sea floor, limestones, shales, sandstones, have been metamorphosed into marbles, schists, and quartzites, harder and more crystalline than their original forms. In some areas, temperatures became high enough to cause partial melting, creating magmas that rose through the crust and cooled to form granite plutons and volcanic rocks. Evidence of this magmatism is found throughout the Himalayas, particularly in the higher elevations where deeply buried rocks have been exhumed by erosion and now lie exposed at the surface. These igneous rocks tell us that the collision generated not just mountains, but also intense thermal and chemical processes deep underground. The Tibetan Plateau, which lies north of the Himalayan peaks, is another consequence of the India-Asia collision. As India pushed into Asia, it did not just create a narrow belt of mountains, but also affected a vast area of the Asian continent, hundreds of miles north of the collision zone. The crust in this region thickened, not through folding and thrusting that characterizes the Himalayas, but through other mechanisms that are still being studied and debated. The result is a plateau averaging about 15,000 feet in elevation, an area the size of Western Europe standing at elevations where most mountains have their summits. The Tibetan Plateau is often called the third pole because of the amount of ice it contains and the influence it has on global climate. The formation of the plateau has had profound effects on Asian and global climate. The high elevation affects atmospheric circulation, creating barriers to airflow, forcing the jet stream to split and flow around the plateau. The elevation also affects the development of the summer monsoon, the seasonal wind pattern that brings moisture-laden air from the Indian Ocean inland across India and Southeast Asia. The monsoon is intensified by the presence of the Tibetan Plateau, which heats up in summer and creates a low-pressure system that draws moist air inland. This monsoon is critical to agriculture and water supply for more than 1 billion people, and its strength and reliability are directly linked to the existence and elevation of the plateau. The collision between India and Asia is ongoing. GPS measurements show that India continues to move northward at about 2 inches per year, and this motion shows no sign of stopping. As long as the motion continues, the Himalayas will continue to rise, the plateau will continue to be elevated, and the tectonic stresses will continue to build, eventually being released in earthquakes. The mountains we see today are not the final form, not the end product of the collision, but rather a snapshot of an ongoing process that has tens of millions of years yet to run. The question of when the collision will end is impossible to answer with certainty. It depends on factors deep within the Earth, on the forces driving plate motion, on the configuration of convection sails in the mantle, on processes that we do not fully understand. Some models suggest that the collision could continue for another 50 million years or more, gradually slowing as the kinetic energy of India's motion is dissipated, as the forces driving the plates weaken, as the system reaches a new equilibrium. Other models suggest that changes in plate boundaries elsewhere might redirect India's motion, might change the geometry of the collision, might even reverse the process and begin pulling the continents apart again. But these are speculations about a distant future. For now, in the present, the collision continues, the mountains rise, and the evidence of this ongoing process is visible throughout the Himalayas.
The folded rock layers, the thrust faults, the metamorphic minerals, the earthquakes that regularly shake the region, all are testament to the power of the India-Asia collision, to the forces that created and continue to shape the roof of the world. Understanding this collision, this continental convergence, changes how you see the mountains. They are not simply beautiful landscapes or challenging climbs. They are expressions of fundamental Earth processes, manifestations of plate tectonics, examples of what happens when immense forces act on continental crust over geologic time. To look at the Himalayas is to look at the consequences of collision, to see what continents do when they meet, to witness the transformation of horizontal seafloor sediments into vertical mountain peaks. It is a lesson in geology written at a scale that cannot be ignored, that commands attention, that demands that we reconsider our assumptions about the permanence of landscapes and the stability of the earth beneath our feet.
The mechanism by which mountains rise from colliding continents is both simple in principle and complex in detail. The principle is straightforward. When continental crust is compressed, it thickens, and because it is buoyant, it rises. But the details involve intricate interactions between different types of deformation, different rock properties, different thermal regimes, and different timescales. To understand how the Himalayas have risen to their current heights requires understanding these mechanisms, requires seeing how rock responds to force, how mountains grow millimeter by millimeter over millions of years. Crustal thickening is the primary mechanism. Normal continental crust is about 20 to 25 miles thick. Beneath the Himalayas and the Tibetan Plateau, the crust has been thickened to as much as 40 to 50 miles. This thickening occurs through a combination of processes. Thrust faulting stacks rock layers on top of each other, literally piling up the crust. Folding concentrates rock into smaller horizontal areas, increasing thickness. And ductile flow at deeper levels, where temperature and pressure are high enough that rock behaves more like a very viscous fluid, redistributes material, moving it from areas of compression to areas where it can more easily accommodate. The thickened crust is less dense than the underlying mantle, so it floats higher, much like a thick piece of wood floats higher in water than a thin piece. This principle, called isostasy, explains why thickened crust stands high. The Himalayas are elevated not because rock has been piled on top of the surface, but because the crust beneath them has been thickened, increasing the buoyancy and forcing the surface upward. The visible mountains are just the top part of a much thicker crustal root that extends deep into the earth. However, isostasy alone does not explain all of the Himalayas' elevation. The mountains are higher than simple isostatic balance would predict, suggesting that other forces are at play. One such force is the continuing compression from India's northward push. This compression actively pushes the mountains upward, maintaining elevations above what isostasy alone would support. The mountains are being squeezed upward, forced higher by horizontal forces converted into vertical motion. Another factor is the resistance of the crustal root to sinking into the mantle. While the crust is less dense than the mantle and thus buoyant, it is also being pushed down by the weight of the mountains above. There is a balance between the buoyancy trying to push the crust up and the weight trying to push it down. The exact elevation of the mountains at any given time depends on this balance, which can shift as conditions change. The rate of uplift in the Himalayas varies across the range and over time. GPS measurements, which can detect vertical motion with millimeter precision, show that some areas are rising at rates of 3 to 10 millimeters per year. This is actual uplift, the rock moving upward relative to the center of the Earth. But this uplift is not the same as an increase in elevation because erosion is simultaneously removing material from the surface. If erosion removes rock at the same rate or faster than uplift raises it, the elevation stays the same or decreases even though the rock is rising. This interplay between uplift and erosion is crucial to understanding mountain evolution. In the Himalayas, erosion rates are among the highest on Earth, with some river systems removing rock at several millimeters per year averaged across their drainage basins. This rapid erosion is driven by the steep slopes, the abundant precipitation from the monsoon, and the presence of glaciers that are effective at quarrying and transporting rock. The erosion keeps pace with uplift, preventing the mountains from growing indefinitely, maintaining a rough equilibrium between building and wearing away. Interestingly, erosion can actually drive further uplift through a process called isostatic rebound. When rock is removed from the surface by erosion, the weight pressing down on the crust is reduced. The crust responds by rising, much like a boat rises higher in the water when cargo is removed. This means that areas experiencing rapid erosion can also experience rapid uplift, even if the tectonic forces driving the initial mountain building have weakened. Some research suggests that the highest peaks in the Himalayas, which are also areas of very rapid erosion, may be elevated in part by this isostatic response to erosion. The concept of isostatic rebound challenges the intuitive notion that erosion simply lowers mountains. While erosion does remove rock from the surface, it also triggers a response from the crust that can bring deeper rock upward, partially offsetting the surface lowering. The net effect is that mountains erode more slowly than they would if isostasy did not operate. This is one reason why mountain ranges can persist for tens of millions of years, even in the face of vigorous erosion. The different rock types in the Himalayas respond differently to the forces acting on them. Some rocks are brittle, fracturing and faulting when stressed. Others are ductile, flowing and folding without breaking. The behavior depends on temperature, pressure, the type of rock, and how quickly stress is applied. Near the surface, where temperatures are low, rocks tend to be brittle and deformation occurs primarily through faulting. At depth, where temperatures are high, rock can flow and deformation occurs through folding and ductile shearing.
This difference in behavior with depth creates a layered structure in the crust, with brittle deformation at shallow levels and ductile deformation at depth. The transition between these two regimes, called the brittle ductile transition, occurs at depths of about 10 to 15 kilometers in the Himalayas, depending on the local thermal structure and rock type. This transition is significant because it affects how stress is distributed and released, influencing where earthquakes occur and how the crust deforms over long timescales. Metamorphism, the transformation of rock by heat and pressure, plays a crucial role in mountain building. As rocks are buried during crustal thickening, they are heated and compressed, causing their minerals to recrystallize into new forms more stable under the new conditions. This metamorphism can strengthen rocks, making them more resistant to deformation, or it can weaken them, making them more prone to flow. The balance between these effects influences how the crust responds to continued compression. In the highest parts of the Himalayas, rocks have been metamorphosed to high grades, forming gneisses and schists with minerals like garnet, kyanite, and sillimanite that indicate formation at temperatures of 500 to 700 degrees Celsius and pressures corresponding to depths of 15 to 25 kilometers. These rocks have since been brought to the surface by uplift and erosion, exposing what was once deep crust. The presence of these high-grade metamorphic rocks at the surface tells us that the Himalayas have experienced enormous amounts of both burial and exhumation, that rock has been cycled from depth to surface over the course of the collision.
The uplift of the Himalayas is not uniform in time. Evidence suggests that uplift rates have varied over the 50 million years since collision began, with periods of rapid uplift alternating with periods of slower rise. These variations may be linked to changes in the rate of India's northward motion, to changes in climate that affected erosion rates, to reorganizations of the deformation field as different structures formed and were later abandoned. Understanding these temporal variations is an active area of research, with scientists using dating techniques applied to rocks exhumed from depth to reconstruct the uplift history. One of the challenges in studying Himalayan uplift is distinguishing between rock uplift and surface uplift. Rock uplift refers to the movement of rock relative to the center of the Earth. Surface uplift refers to the change in elevation of the land surface. These are not the same if erosion is occurring. A rock particle can be moving upward, rock uplift, while the surface is being lowered by erosion, negative surface uplift. Many studies measure rock uplift by dating when rocks cooled as they were brought closer to the surface, while studies of surface uplift look at changes in the elevations of markers like river terraces or lake shorelines. GPS networks installed across the Himalayas have revolutionized the study of present-day motion, providing continuous measurements of both horizontal and vertical displacement. These data show that the mountains are rising, that the deformation is ongoing, that the collision continues to reshape the landscape. But the GPS record is short, only a few decades long, and cannot tell us whether current rates are typical of the long-term average or represent a temporary fluctuation. Combining GPS data with geological evidence of long-term uplift rates allows a more complete picture to emerge. The silent growth of the Himalayas, silent because it occurs too slowly to perceive without instruments, is the cumulative result of countless small motions, each contributing a millimeter here, a millimeter there, adding up over time to kilometers of elevation. This growth is not smooth or continuous, but is punctuated by earthquakes when accumulated stress is suddenly released, by landslides when slopes become too steep, by glacial advances and retreats that modulate erosion rates. The mountains rise in fits and starts, in response to forces that vary on timescales from seconds, earthquake ruptures, to millions of years, plate tectonic motions. Understanding uplift mechanisms is not just an academic exercise. It has practical implications for assessing seismic hazards, for understanding how erosion and sedimentation affect river systems and water resources, for predicting how climate change might affect mountain landscapes. The Himalayas are home to hundreds of millions of people, are the source of water for billions more, and are a region of active natural hazards. Knowing how and why the mountains rise, how they are shaped by erosion, how they respond to external forces, this knowledge can help societies adapt to the challenges of living in and depending on one of Earth's most dynamic landscapes. As you continue your ascent through the mountains, gaining elevation, following trails that climb through forests and across glacial valleys towards the high passes and the peaks beyond, you are moving through this machinery of uplift, experiencing the vertical dimension that is the consequence of collision. Every meter you climb is a meter that was once at a lower elevation, that has been lifted by the forces we have been describing, that represents the cumulative effect of millions of years of compression and thrust faulting and isostatic adjustment. The effort required to gain elevation is tiny compared to the forces required to lift rock, but it gives a physical sense of the vertical scale, of what it means for mountains to rise miles into the sky.
Mount Everest stands at 29,032 feet above sea level, according to the most recent official measurement, agreed upon by China and Nepal in 2020. This makes it the highest point on Earth's surface, the apex of the planet's topography, the ultimate expression of the forces that have been building the Himalayas for 50 million years. But Everest is more than just the highest mountain. It is a geological monument, a natural archive, a place where the history of the India-Asia collision is written in stone and preserved at elevations where few can read it, but where, for those who understand the language, the story is remarkably complete. The mountain has 3 names, each reflecting a different cultural perspective. Everest is the English name, given by the British during their surveys of India in the 19th century, honoring George Everest, the Surveyor General of India. Sagarmatha is the Nepali name, meaning forehead of the sky, or alternatively, goddess of the sky, depending on interpretation. Chomolungma is the Tibetan name, meaning mother goddess of the world, or goddess mother of the mountains. Each name carries significance, each reflects a relationship with the peak, and using all 3 acknowledges that this mountain belongs to multiple cultures, that it holds meaning beyond its physical reality. The geology of Everest is complex, reflecting the mountain's position at the boundary between different tectonic units, its exposure to extreme conditions, and its long history of deformation and uplift. The summit pyramid, the distinctive triangular peak visible in photographs, is composed of Ordovician limestone, rock that was deposited on the floor of the Tethys Sea approximately 470 to 450 million years ago. This limestone contains fossils of marine organisms, crinoids, trilobites, brachiopods, creatures that lived in a warm, shallow sea that existed long before India began its northward journey. The presence of marine fossils at Everest's summit is one of the most remarkable facts in geology. These fossils tell us that the rock forming the highest point on Earth was once underwater, that it has been lifted nearly 6 miles vertically from its original position at or below sea level. The uplift represents one of the most extreme examples of vertical crustal movement anywhere on the planet, a testament to the power of tectonic forces, a demonstration that even the seafloor can be elevated to the height of the highest mountains given sufficient time and force. Below the summit limestone lie other rock units, each with its own history, each representing different episodes in the long story of this region. The Everest series, which forms much of the upper part of the mountain, consists of metamorphosed sedimentary and igneous rocks that were strongly deformed during the collision. These rocks show evidence of having been heated to temperatures exceeding 600 degrees Celsius and compressed at pressures equivalent to being buried 15 to 20 kilometers deep. They have since been exhumed, brought to the surface by a combination of uplift and erosion, their minerals and structures providing clues about the conditions they experienced during the collision. The yellow band, a distinctive layer of metamorphosed limestone, visible as a golden stripe near the summit, is a marker horizon used by climbers to gauge their progress during the final push to the top. This band represents a particular stratigraphic level in the Ordovician sequence, a layer that was slightly different in composition from the rocks above and below it, differences that were enhanced by metamorphism and that now make it stand out visually. The yellow band is also significant geologically because it can be traced across much of the Everest region, allowing geologists to correlate rock units and reconstruct the structural history of the area. Everest sits at the intersection of 2 major tectonic structures, the South Tibetan Detachment, a low-angled normal fault that bounds the top of the mountain, and the main central thrust, a major thrust fault that runs through the lower parts of the peak. These faults accommodated different types of motion during the collision. The thrust fault represents compression, with rock being pushed upward and southward.
The detachment represents extension, with the upper part of the mountain sliding eastward relative to the lower part. The interaction between these two faults is complex and not fully understood, but it is clear that both played roles in bringing the rocks that now form Everest to their current positions. The question of why Everest is the highest peak is interesting and not entirely answered. One factor is its position near the center of the Himalayan arc, where the collision is most direct, where the compression is greatest. Another factor is the configuration of the underlying structures, the faults and folds that have concentrated uplift in this particular location. A third factor may be erosion, or rather the relative lack of it on Everest compared to other peaks. Everest lies in a region where the monsoon is somewhat weaker, where precipitation is less, where glacial erosion is less aggressive. This may have allowed Everest to maintain its height, while other peaks subjected to more vigorous erosion have been cut down. But Everest is not static. The mountain continues to rise, continues to be pushed upward by the ongoing collision. GPS measurements are difficult to obtain on Everest's summit due to the extreme conditions, but measurements on nearby peaks and at lower elevations show uplift rates of several millimeters per year. If Everest is rising at similar rates, and there is no reason to think it is not, then the mountain is gaining elevation, though how much of this translates to an increase in summit elevation depends on erosion rates, which are hard to quantify at such extreme heights. Climbing Everest is, in a sense, a journey through geological time. Starting from base camp at about 17,000 feet on the Nepali side, climbers ascend through progressively older rock units, moving from younger sediments deposited after the collision began, through the metamorphosed rocks that record the collision itself, to the ancient seafloor sediments at the summit. Each camp, each landmark along the route, the Khumbu Icefall, the Western Khum, the Lhotse Face, the South Col, the Hillary Step, which collapsed in the 2015 earthquake, and the Summit Ridge, pass through different geological units, each with its own story.
The climbers are usually not thinking about geology. They're focused on survival, on managing the extreme cold, the low oxygen levels, the physical exhaustion, the dangers of crevasses and avalanches and falls. But they are, nonetheless, moving through a landscape that is a textbook of mountain building processes, that preserves evidence of events spanning hundreds of millions of years, that connects the ocean floor to the sky. The summit they strive to reach is made of seafloor, lifted by collision, shaped by erosion, standing as the highest point on Earth, not because it is special in any fundamental way, but because the interplay of tectonic forces, rock properties, and erosion patterns happen to produce maximum elevation at this particular location. The summit itself is a small area, just large enough for a few people to stand, covered by snow and ice that mask the underlying rock. Climbers do not spend long there. The conditions are too extreme, the oxygen too scarce, the cold too penetrating. They take photographs, plant flags, savor the achievement, and then descend as quickly as safely possible. But those few minutes at the summit are spent at the highest point on the planet's solid surface, at the apex of the Himalayas, at the place where the collision between India and Asia has produced maximum vertical displacement. The view from Everest's summit, on the rare occasions when weather permits visibility, is of other peaks, hundreds of them, stretching in every direction, ridge after ridge of mountains extending to the horizon. You can see Lhotse, the fourth highest mountain, immediately adjacent to Everest, sharing a ridge with it for part of the way up. You can see Makalu to the east, Cho Oyu to the west, and on exceptionally clear days, Kangchenjunga far to the southeast.
The view encompasses dozens of 7,000-meter peaks, hundreds of 6,000-meter peaks, a landscape of mountains that seems infinite, that confirms what standing at the summit makes viscerally clear. You are at the center of the most spectacular mountain range on Earth. But more than the visual spectacle, more than the achievement of reaching the summit, Everest represents something profound about our planet. It shows us that Earth is active, that its surface is not fixed, but is constantly being reshaped by internal forces, that processes operating over millions of years can produce effects as dramatic as lifting ancient seafloor to the height of commercial aircraft cruising altitude. Everest is a product of plate tectonics, of continental collision, of the slow but inexorable motion of continents that continues today and will continue into the distant future. The mountain also represents the limits of human capability. Despite modern equipment, despite bottled oxygen, despite fixed ropes and established camps, Everest remains dangerous, remains challenging, remains a place where people die regularly in the attempt to reach the summit. The death zone, above 26,000 feet, is a region where the human body cannot survive for extended periods, where even with supplemental oxygen, the body is slowly dying, where decisions must be made quickly because cognitive function is impaired. Everest tests physical and mental limits, pushes climbers to the edge of what is possible. Yet hundreds of people now summit Everest each year during the brief weather windows in May and sometimes October when conditions are most favorable. The mountain has become commercialized, with guiding companies charging tens of thousands of dollars to lead clients to the summit, with traffic jams reported near the top as climbers queue to traverse the final ridge. This democratization of Everest is controversial, with some arguing that it diminishes the achievement, that it leads to environmental degradation, that it puts people at risk who are not adequately prepared. Others argue that access should not be restricted to elite climbers, that the mountain belongs to all who wish to attempt it, that commercial expeditions make the summit accessible to people who would otherwise never have the chance. The debate over Everest's commercialization is beyond our scope here, but it reflects a broader tension about how we relate to these mountains, what they mean to us, what uses are appropriate. Are the Himalayas sacred spaces, to be protected and minimally impacted? Are they playgrounds for adventure, resources to be exploited for tourism? Are they geological laboratories, places of scientific study? They are, of course, all of these and more, and balancing these different values and uses is an ongoing challenge. What is certain is that Everest, and the Himalayas more broadly, will continue to draw humans, will continue to inspire and challenge and teach. The mountains are not just obstacles to be overcome or summits to be collected. They are part of Earth's story, part of the ongoing narrative of our planet's evolution. To understand them, to study them, to experience them is to connect with deep time, with processes that dwarf human concerns, with a perspective that can change how we see ourselves and our place in the universe. Everest is the highest point, yes, but it is also a symbol, a representation of the forces that shape worlds, a reminder that our planet is alive, dynamic, and full of wonders that reward patient attention and humble inquiry.
The monsoon that sweeps across South Asia each summer is one of the planet's most significant climate patterns, affecting more than 1 billion people, delivering water that sustains agriculture, fills rivers, recharges aquifers. The monsoon is a seasonal wind reversal, driven by differential heating between land and ocean that brings moist air from the Indian Ocean northward across the subcontinent. And the monsoon exists in its current form largely because of the Himalayas, because of the presence of this enormous mountain barrier that affects atmospheric circulation, that creates the conditions necessary for the monsoon to develop and persist. Without the Himalayas, the monsoon would be weaker, less reliable, less extensive. The mountains force the moist air to rise, cooling it, causing water vapor to condense and fall as rain. The southern slopes of the Himalayas receive some of the highest rainfall on Earth, with places like Cherrapunji in the Meghalaya hills of northeast India recording annual rainfall exceeding 450 inches, nearly 40 feet of rain in a single year. This extraordinary precipitation is a direct consequence of the topography, of the mountains forcing air upward, wringing moisture from it, creating conditions where rainfall is intense and sustained. The rain that falls on the Himalayas is not just a climatic phenomenon, but also a geological agent, a force that shapes the mountains even as the mountains shape the monsoon. Water is perhaps the most effective erosive agent on Earth's surface, capable of dissolving rock, of transporting sediment, of cutting valleys and gorges, of moving mountains grain by grain. The Himalayas, receiving heavy precipitation, are being eroded rapidly, with river systems removing vast quantities of sediment each year, carrying it down to the plains and ultimately to the ocean. The relationship between the monsoon and the mountains is complex and bidirectional. The mountains create the monsoon by blocking airflow, by creating a thermal low pressure over the Tibetan Plateau in summer that draws moist air inland. The monsoon, in turn, affects the mountains by delivering precipitation that drives erosion, that shapes the landscape, that determines how the mountains evolve. This feedback between climate and tectonics is a topic of active research, with scientists trying to understand how changes in mountain height affect climate and how changes in climate affect the evolution of the mountains. One hypothesis suggests that the uplift of the Himalayas and the Tibetan Plateau intensified the monsoon, creating a positive feedback where higher mountains led to more rain, which led to more erosion, which paradoxically led to more uplift through isostatic rebound, which further intensified the monsoon. This feedback may have been important in establishing the current monsoon pattern, which has been operating for several million years, but which may have been different in the more distant past when the mountains were lower. The monsoon also affects the distribution of precipitation across the Himalayas. The southern slopes, facing the oncoming monsoon winds, receive far more rain than the northern slopes, which lie in the rain shadow of the range. This creates a stark climatic divide, with lush green landscapes on the south giving way to arid desert-like conditions on the north, sometimes within just a few miles of horizontal distance, but separated by thousands of feet of elevation and the barrier of the range. The Tibetan Plateau, lying north of the Himalayas, is a high-altitude desert, receiving only a fraction of the precipitation that falls on the southern slopes. This precipitation gradient has profound effects on erosion rates. The southern slopes, with their heavy rainfall, are being eroded rapidly, with rivers cutting deep gorges, with landslides frequent, with the landscape changing visibly on human timescales. The northern slopes, with less precipitation, erode more slowly, maintaining steeper average slopes, with the landscape more stable, less dynamic. This difference in erosion rates affects how the mountains evolve, potentially causing the range to migrate southward over geological time, as the southern side is cut back faster than the northern side rises. The rivers that drain the southern Himalayas are among the most sediment-laden rivers in the world. The Brahmaputra, the Ganges, and the Indus together carry more than 1 billion tons of sediment to the ocean each year, material eroded from the mountains, transported across the plains, deposited in deltas or carried out to sea. This sediment represents the mountains being worn away, represents rock that was uplifted and is now being returned to lower elevations, eventually perhaps to be subducted and recycled into new mountains in some distant future. The sediment load of these rivers affects everything downstream. The rivers change course frequently as channels fill with sediment and new channels are cut. Floods are common, particularly during the monsoon when river discharge increases dramatically. Deltas grow, extending into the ocean, building new land from the eroded mountains. The Ganges-Brahmaputra Delta, the world's largest, is a direct product of Himalayan erosion, a landscape created from mountains destroyed, a low-lying plain built from high peaks.
But sediment is not just a geological product, it is also a resource, and sometimes a hazard. The fertile soils of the Indo-Gangetic Plain, which support hundreds of millions of people, are derived from Himalayan sediments.
The minerals in these sediments provide nutrients for crops, making the plain one of the most productive agricultural regions on Earth. But the same sediment fills reservoirs, reducing their capacity, shortening their lifespans. It clogs irrigation canals, requiring constant maintenance. It buries fields during floods, sometimes damaging crops, other times enriching soils with new nutrients. The glaciers that mantle the higher elevations of the Himalayas are another consequence of precipitation and altitude. Snow that falls at high elevations accumulates, compacts, and transforms into glacial ice. The ice flows downslope under its own weight, carving valleys, plucking rock from the walls, grinding sediment into fine powder. The glaciers are important both as sculptors of the landscape and as water resources, storing precipitation as ice during winter and releasing it as meltwater during summer, providing steady water flow to rivers that might otherwise run dry during the non-monsoon months. Climate change is affecting the monsoon and the glaciers, with consequences that are not fully understood but that are clearly significant. The monsoon pattern is shifting, with some regions receiving more precipitation and others less, with the timing of the monsoon changing, with greater year-to-year variability making agriculture more challenging. The glaciers are retreating, losing mass, some of them dramatically, exposing new landscapes, altering river flows, creating hazards like glacial lake outburst floods, where meltwater accumulates behind unstable moraines and then suddenly releases, sending floods downstream that can be catastrophic. These changes affect hundreds of millions of people who depend on Himalayan water resources. The rivers that originate in the Himalayas provide water for drinking, for irrigation, for industry, for hydroelectric power generation. Changes in the timing or quantity of this water affect food security, economic development, political stability. The Himalayas are sometimes called the water tower of Asia because they store water as snow and ice and release it gradually, feeding the major river systems of the continent. If this water tower is affected by climate change, the consequences extend far beyond the mountains themselves. The monsoon also affects the Himalayas through its influence on erosion patterns and rates. Research suggests that periods of intense monsoon are associated with increased erosion, which can trigger increased uplift through isostatic rebound, which can influence tectonic processes. The connections are complex and not fully understood, but it is clear that climate and tectonics are not independent, but interact, affecting each other in ways that shape mountain evolution. Understanding the relationship between the monsoon and the mountains requires integrating knowledge from multiple disciplines: climatology, hydrology, geology, ecology. The system is complex, with many feedbacks and interactions, with processes operating on timescales from days, individual monsoon pulses, to millions of years, long-term climate and tectonic evolution. The Himalayas are not just a geological feature, but are intimately connected to the climate system, to the water cycle, to the ecosystems and human societies of South Asia. They are part of an integrated Earth system, where changes in one component affect others in ways that are sometimes predictable and sometimes surprising. As you traverse the Himalayas, moving from the southern slopes to the northern, you experience this climatic gradient directly. The vegetation changes from dense forests on the south to scrubby alpine plants, and then to nearly barren rock and ice on the highest peaks, and finally to the high-altitude desert of the plateau. The rivers change from raging torrents on the south to smaller, clearer streams on the north. The air changes from humid and often clouded on the south to dry and brilliantly clear on the north. This transect across the range is a transect across climate zones, a journey from monsoon-influenced landscapes to rain-shadow-affected ones, a demonstration of how mountains create and are created by climate,
how the solid earth and the atmosphere interact to shape the world we inhabit. The monsoon's role in sculpting the Himalayas is ongoing, is visible in the present-day landscape, is part of the active processes that continue to shape these mountains. The relationship between climate and mountains is not a historical curiosity, but a current reality, with implications for how we understand Earth systems, how we predict future changes, how we manage resources and hazards in one of the most densely populated regions of the planet. The monsoon and the mountains are partners in an ancient dance, each influencing the other, each responding to changes in the other, creating together the landscape and climate of South Asia.
Rivers are perhaps the most effective sculptors of mountains, cutting through rock with a patience and persistence that eventually wears down even the highest peaks. In the Himalayas, the major rivers, the Indus, the Ganges, the Brahmaputra, and their countless tributaries, have carved some of the deepest gorges on Earth, creating landscapes of extraordinary vertical relief where river valleys lie thousands of feet below the peaks that tower above them. But what makes the Himalayan rivers especially remarkable is that many of them are older than the mountains themselves, a fact that seems paradoxical until you understand the concept of antecedent drainage. An antecedent river is one that established its course before the landscape rose around it. As the land uplifts, the river maintains its path, cutting downward at a rate that keeps pace with or exceeds the rate of uplift, eventually creating a gorge through the rising mountains. In the Himalayas, several major rivers are antecedent, having originated on the northern side of the collision zone and flowing southward across what was then relatively flat terrain. As the mountains rose, these rivers continued flowing in their established courses, cutting through the rising rock, creating the trans-Himalayan gorges we see today. The Indus is perhaps the clearest example. This river originates on the Tibetan Plateau, flows northwest along the northern edge of the range, and then turns sharply southwest, cutting through the western Himalayas in a series of spectacular gorges before emerging onto the plains of Pakistan. The fact that the Indus crosses the Himalayan range rather than being deflected around it suggests that the river was already flowing in this direction when the mountains began to rise, that it was able to maintain its course by cutting downward as the land rose upward. Similarly, the Brahmaputra originates on the Tibetan Plateau, flows east along the northern side of the range, and then makes a dramatic hairpin turn, cutting through the eastern Himalayas in one of the deepest gorges on Earth before emerging into the plains of Assam and Bangladesh. The gorge section, where the river flows between Namche Barwa and Gyala Peri, two peaks each exceeding 25,000 feet, represents a vertical relief of nearly 20,000 feet from the peaks to the river, one of the greatest relief features anywhere on the planet. These gorges are not static features, but are active sites of erosion, where the rivers are still cutting downward, where landslides and rockfalls constantly reshape the valley walls, where the landscape is dynamic and hazardous. The rivers carry enormous sediment loads, material eroded from the gorge walls and from upstream sources, transported downstream toward the ocean. The water in these rivers is often opaque, clouded with suspended sediment, colored brown or gray by the rock particles it carries. The ability of rivers to cut through rising mountains depends on several factors. The river must have sufficient discharge, sufficient volume of flowing water to transport sediment and to erode bedrock. The bedrock itself must be erodible, must be susceptible to the abrasive action of water and sediment. And the rate of downcutting must equal or exceed the rate of uplift. Otherwise, the river would be defeated by the rising land, would be ponded or diverted, would lose its ability to maintain its course. In the Himalayas, all these conditions are met. The rivers have high discharge, fed by monsoon rains and by glacial melt. The rocks, while hard, are fractured and weakened by tectonic deformation, making them more susceptible to erosion.
and the rivers are steep, descending thousands of feet in just a few miles, giving the water tremendous energy to cut and transport. The result is that the rivers can keep pace with uplift rates of several millimeters per year, maintaining their courses through the rising mountains. But not all rivers are antecedent. Some of the tributaries of the major rivers have courses that are clearly controlled by the structure of the mountains, flowing along valleys that follow faults or weak rock layers, creating dendritic drainage patterns that reflect the underlying geology. These rivers post-date the mountain building, having established their courses after the major uplift had created the topography. They are consequent rivers, following paths determined by the existing landscape. The interplay between antecedent and consequent drainage creates the complex network of rivers that characterizes the Himalayas. The major trans-Himalayan rivers cut across the grain of the mountains, creating through-going valleys that provide routes for travel and trade, though often difficult and dangerous routes. The tributary rivers follow the grain, creating longitudinal valleys that run parallel to the mountain ranges, separated by high ridges. This pattern of drainage is both a consequence of and a control on how the mountains evolve, with erosion focused in certain areas, with sediment transport pathways established, with the landscape being sculpted into its current form. The gorges cut by these rivers are environments of extreme relief and constant change. The walls are steep, often nearly vertical, composed of rock that is fractured and unstable. Landslides are common, triggered by earthquakes, by heavy rains, by undercutting of slopes by the river. Some landslides are small, involving just a few cubic meters of rock. Others are massive, involving millions of cubic meters, creating temporary dams that block the river, forming lakes that eventually breach catastrophically, sending floods downstream that can be devastating.
One such event occurred in 2000 when a massive landslide blocked the Yigong River, a tributary of the Brahmaputra in eastern Tibet. The landslide created a lake that filled rapidly, eventually breaching and releasing a flood that traveled hundreds of miles downstream, affecting communities in Tibet and India. The flood peak was estimated at more than 1 million cubic feet per second, one of the largest discharge events recorded in the region. Such events are not rare, but occur periodically, reshaping the river valleys, creating hazards for downstream populations, demonstrating the dynamic nature of these landscapes. The sediment transported by Himalayan rivers is not just carried to the ocean, but is also deposited along the way, creating features that record the history of erosion and deposition. River terraces, flat benches that stand above the current river level, represent former floodplains that have been abandoned as the river cut downward, lowering its channel. By dating these terraces, geologists can determine how fast the river has been cutting down, can reconstruct the uplift history of the region, can understand how erosion rates have varied over time. Some rivers have cut through bedrock to depths of thousands of feet, creating narrow gorges where the river occupies the entire valley floor, where there is no space for terraces or floodplains. These bedrock gorges are sites of extremely rapid erosion, where the river is actively lowering its bed, where the balance between uplift and erosion is playing out in real time. GPS measurements in these gorges show that the valley floors are rising even as the rivers cut downward, indicating that uplift rates exceed erosion rates, that the mountains are still growing, even in the places where erosion is most focused. The power of flowing water to shape landscapes is nowhere more evident than in the Himalayan gorges. Water that seems soft, that yields to touch, becomes a cutting tool when moving fast and carrying sediment. The abrasive action of sand and gravel in fast-flowing water can cut through the hardest rock given time. The chemical action of water can dissolve minerals, widening cracks, weakening stone. And the force of water during floods can move boulders weighing tons, can reshape entire valley floors in hours, can accomplish in brief, violent episodes what might take centuries during normal flow. The rivers also transport nutrients and organic matter, connecting different parts of the ecosystem,
bringing fertility from the mountains to the plains. The sediments deposited by rivers create the rich soils of the floodplains and deltas, soils that have supported agriculture and civilization for thousands of years. The Ganges Plain, one of the most densely populated regions on Earth, owes its fertility to Himalayan erosion, to the sediment delivered by rivers, to the nutrients derived from weathered mountain rock. But the rivers also pose hazards. Floods are common, particularly during the monsoon, when discharge can increase tenfold or more in a matter of hours. Flash floods in tributaries can catch people unawares, sweeping away bridges, roads, and entire villages. Erosion of riverbanks undermines structures, forces relocations, creates instability. The same forces that create fertile plains also create risks, and managing these risks is an ongoing challenge for the millions who live in and depend on these river systems. The relationship between rivers and mountains is symbiotic and dynamic. The mountains create the elevation gradients that give rivers their power, that provide the sediment they transport. The rivers erode the mountains, shaping their form, influencing their evolution, participating in the balance between uplift and denudation. Without rivers, the mountains would be different, higher perhaps, but also different in form, less dissected, with different patterns of ridges and valleys. The mountains and rivers co-evolve, each affecting the other, creating together the landscape we see today. As you follow a trail that runs alongside one of these rivers, you experience this relationship directly. The sound of the water is constant, a roar or rush or gurgle depending on gradient and volume. The air is humid, cooler near the water, carrying the smell of wet rock and vegetation. The river itself is visible in glimpses through the trees or as an open expanse where the valley widens, the water moving always down slope, always transporting, always working to lower the mountains and carry them to the sea. This is the river's work, and it has been ongoing for millions of years, and it will continue as long as rain falls and gravity pulls water down slope.
Ice is a sculptor of landscapes, shaping mountains in ways that water alone cannot. Glaciers form where snowfall exceeds melting, where winter's snow survives the summer and accumulates year after year, compacting under its own weight, transforming from fluffy snow to granular fern to solid ice. This ice, once thick enough, begins to flow under the pull of gravity, moving slowly down slope, carving the valleys through which it flows, creating some of the most distinctive landforms in mountain regions. The Himalayas contain thousands of glaciers, ranging from small cirque glaciers occupying high alpine bowls to massive valley glaciers extending for dozens of miles, to the enormous ice sheets that mantle parts of the Tibetan Plateau. These glaciers contain a significant fraction of the world's fresh water outside the polar regions, and they play crucial roles in the regional water cycle, in the landscape's evolution, and increasingly in the global conversation about climate change. Glaciers move through a combination of internal deformation and basal sliding. The ice is not rigid, but flows like a very viscous fluid when subjected to pressure. The glacier's surface moves faster than its base, creating internal stresses and crevasses where the ice fractures. The base slides over the bedrock, lubricated by meltwater, by clay-rich sediments, by the pressure of the ice above. The rate of movement varies from a few inches to a few feet per day, imperceptible on human timescales, but capable of transporting vast amounts of rock and sediment over decades and centuries. As glaciers flow, they erode the landscape through several mechanisms. Plucking occurs where glacial ice freezes onto bedrock, incorporating chunks of rock that are then pulled away as the ice moves. This process is most effective where the bedrock is already fractured, where joints and cracks provide weaknesses that the ice can exploit.
Abrasion occurs as rock embedded in the base of the glacier grinds against the bedrock, creating scratches called striations and polishing the rock surface to a smooth finish. The sediment produced by this grinding is rock flour, silt-sized particles that give glacial meltwater its distinctive cloudy appearance. The valleys carved by glaciers have a characteristic U-shaped profile, with steep walls and relatively flat floors, distinctly different from the V-shaped profiles of river-carved valleys. This shape results from the glacier's tendency to erode more vigorously at its center, where the ice is thickest and moves fastest, and less vigorously at its margins. The result is a valley with wide, flat floors and steep sides, often with hanging valleys where tributary glaciers entered at higher elevations and have been left perched above the main valley floor as the main glacier carved deeper. The Himalayan glaciers have created landscapes of extraordinary beauty. Cirques, arêtes, horns, technical terms that describe the sculpted forms left by ice. Cirques are amphitheater-like valleys carved into mountainsides where glaciers originate. Arêtes are sharp ridges formed where two cirques erode backward toward each other. Horns are pyramid-shaped peaks formed where three or more cirques erode from multiple sides. Mount Everest itself, with its distinctive pyramidal form, is a classic example of a horn, shaped by glaciers eroding on multiple sides. These glacial landforms are not just aesthetic features, but also records of past glacial extents and climates. During ice ages, when global temperatures were lower and glaciers were more extensive, the Himalayan glaciers advanced far down their valleys, carving more aggressively, leaving behind moraines and other deposits that mark their maximum extents. During warmer periods, the glaciers retreated, exposing the U-shaped valleys and other features they had created. The current glaciers are shadows of their Ice Age predecessors, occupying only the upper portions of valleys that once were filled with ice for their entire lengths. The glaciers are retreating now, losing mass, their termini pulling back up valley, their surfaces lowering. This retreat is documented through repeat photography, through measurements of glacier length and volume, through observations of new land being exposed as ice disappears. The rate of retreat varies from glacier to glacier, with some losing tens of meters of length per year, others losing less. But the overall trend is clear. The Himalayan glaciers are shrinking, a response to rising temperatures, to changes in precipitation patterns, to a climate that no longer supports the ice extents that existed just decades ago.
This retreat has multiple consequences. The immediate consequence is increased meltwater, temporarily increasing river flows, swelling the glacial lakes that form where retreating glaciers leave depressions, creating hazards where these lakes are unstable and prone to breaching. The longer-term consequence is reduced water storage in ice, reduced meltwater contribution during summer months when it is most needed, potentially affecting water supply for the hundreds of millions who depend on Himalayan rivers. The glaciers also affect the rate at which mountains are eroded. Glacial erosion is generally more effective than fluvial erosion, able to remove more rock per unit time. This means that glaciated valleys erode faster than non-glaciated valleys, influencing the overall evolution of the mountain range. Some research suggests that glaciation, particularly the intense glaciation during ice ages, has actually accelerated the erosion of the Himalayas, removing rock faster than it can be replaced by uplift, possibly influencing the maximum height the mountains can achieve. There is a feedback between glaciation and uplift. More uplift creates higher elevations where glaciers can form. More glaciers create more erosion, which removes weight from the crust, which triggers isostatic rebound, which causes more uplift. This feedback may have been important in the evolution of the Himalayas, potentially amplifying the effects of the India-Asia collision, creating higher peaks than would have formed in the absence of glaciation. The glaciers are also ecosystems, supporting life adapted to extreme conditions.
Microorganisms live on and in the ice, obtaining energy from sunlight and from minerals in the rock flour and dust that accumulates on the glacier surface. These organisms, collectively called cryophytes, can cause the glacier surface to darken, which increases heat absorption, which accelerates melting. Another feedback, this one between biology and climate. Birds and insects are occasionally found on glaciers, some having been blown there by wind, others apparently living on the margins where ice meets rock. Traversing a glacier is a unique experience, requiring caution and specialized equipment. The surface is slippery, the ice hard and unforgiving. Crevices, hidden by snow bridges, pose deadly hazards capable of swallowing climbers into abysses hundreds of feet deep. The cold is penetrating, the wind often intense, the sun reflecting off the ice and snow with a glare that can cause snow blindness without proper protection. Yet the beauty is undeniable. The blue ice revealed in crevice walls, the sculptured forms of ice towers and ridges, the vast white expanses extending toward distant peaks. The glaciers connect us to climate, to the cycles of ice ages and interglacials that have characterized Earth's recent history, to the ongoing changes in our climate system that are affecting these ice masses in real time. They are both ancient, some of the ice may be hundreds or thousands of years old, and ephemeral, likely to disappear within decades or centuries if current trends continue. They are part of the mountain's story, shapers of the landscape, influencers of the water cycle, indicators of climate, beautiful and dangerous and vulnerable. As you stand on the moraine of a retreating glacier, looking up at the diminished ice tongue that once extended far beyond where you now stand, you can see the story written in the landscape. The polished bedrock, the striations, the moraines marking former ice extents, the fresh land that has only recently emerged from beneath the ice, all tell of a more extensive past, of a time when ice was more prevalent, when the climate was different, when the balance between ice and rock was different from today. The glacier's retreat is not just a physical process, but a narrative, a story of change, of climate warming, of a landscape in transition from an ice-dominated to a rock-dominated state. The glaciers of the Himalayas are monuments to the power of ice, to the slow but effective erosion that occurs when frozen water accumulates to sufficient thickness and flows under its own weight. They are also warnings, indicators of climate change, demonstrations that even features that seem permanent can disappear, can transform, can respond to shifts in the conditions that created and sustained them. Watching a glacier retreat, seeing the ice diminish year by year, is like watching time-lapse footage of landscape change, a process that normally occurs too slowly to perceive, becoming visible, tangible, undeniable.
The story of the Himalayas continues, written in stone, shaped by forces that operate across millions of years, influenced by processes that range from the collision of continents to the formation of a single crystal of ice in a high-altitude snowfield. These mountains are not static monuments, but active landscapes, constantly being built and eroded, responding to forces internal and external, participating in the larger systems that govern our planet's behavior. The silent growth continues, millimeter by millimeter, year by year, invisible to the eye, but measurable by instruments, documented by science, confirmed by the evidence written in rock and ice and water. The Himalayas rise, and in their rising, they teach us about time, about change, about the nature of our planet and our place within it. They remind us that what seems permanent is temporary, that mountains can grow and shrink, that landscapes are fluid on geological timescales, that the solid earth is neither solid nor static, but is alive with movement, with transformation, with the ongoing creativity of natural processes. To stand in the Himalayas, to experience their scale and beauty, to contemplate their history and their future, is to connect with something larger than ourselves, something that transcends individual lives and even entire civilizations.
These mountains were here before we arrived, they will be here after we are gone, and they will continue their slow dance of growth and erosion, rise and fall, creation and destruction, long into a future we cannot imagine. The Himalayas are the roof of the world, and they are still being built, still rising, still growing in silence, still shaping the planet we call home.
The silent growth continues, will continue, invisible to the eye, but real nonetheless, measurable and documented and understood, at least in part, by the patient work of scientists who study these mountains, who deploy GPS receivers to track millimeter-scale motions, who date rocks to determine when they were uplifted, who model the forces that drive collision and the responses that create mountains. The knowledge gained from the Himalayas informs our understanding of mountain building processes everywhere, on Earth and potentially on other planets, teaching us the principles that govern how worlds take shape. But knowledge, while valuable, is not the only gift the Himalayas offer. There is also the direct experience, the visceral encounter with scale and power, the aesthetic appreciation of form and color and light, the spiritual response that mountains have evoked in humans across cultures and throughout history. The Himalayas inspire, challenge, humble, and elevate. They draw us upward, literally in the case of climbers, metaphorically for all who contemplate them. They represent something beyond the everyday, something that transcends the mundane concerns that occupy most of our attention, something that reminds us of capacities and perspectives we might otherwise forget. To witness the Himalayas is to witness Earth being Earth, demonstrating the processes that have shaped our planet for billions of years and will continue shaping it for billions more. The collision of India and Asia is not unique. Continents have collided before and will collide again. But this particular collision, happening now in our time, creating the highest mountains on the modern Earth, is extraordinary, is worthy of study and contemplation and respect. We are privileged to live in an epoch when the Himalayas exist in their current magnificent form, when we can visit them, study them, be transformed by our encounters with them. As the sun sets and the peaks take on the golden and then reddish hues of alpenglow, that magical light that comes after sunset when the peaks still catch the sun's rays while the valleys are in shadow, you feel a gratitude, an appreciation for having been here, for having experienced these mountains, for having learned something of their story. The Himalayas have taught you about time, about change, about forces and processes, about the nature of the planet you inhabit. But they have also taught you about persistence, about the power of gradual processes sustained over immense durations, about how the impossible becomes possible when you have millions of years to work with. The silent growth of the roof of the world is not just a geological fact, but a metaphor, a reminder that important changes often happen too slowly to see, but too powerfully to stop, that patience and persistence can move mountains, that the accumulation of small increments over time can produce transformative results. The mountains rise millimeter by millimeter, and eventually they reach the sky. This is a lesson written in stone, carved in ice, carried by rivers, a lesson available to anyone willing to look, to learn, to contemplate the meaning of these extraordinary peaks. The stars are beginning to appear. First Venus bright in the western sky, then the brighter stars, and eventually the full display of the Milky Way arching overhead. The same stars that looked down on the Tethys Sea, that watched the collision begin, that have witnessed the entire rise of the Himalayas and will witness their eventual reduction to low hills and then to nothing, the cycle continuing, creation and destruction, building and eroding, the endless dance of matter and energy that is the story of worlds. You turn from the view,
Begin the walk back, carrying with you the memory of the peaks, the knowledge you have gained, the perspective you have earned. The Himalayas remain, will remain, their silent growth continuing in your absence, unaffected by whether you witness it or not, proceeding according to laws that operated before life existed and will operate after life is gone. But you have been here, have stood in the presence of the roof of the world, have added your own brief moment to the countless moments that make up the human relationship with these mountains, a relationship that is part of their story, just as they now are part of yours. The Himalayas are still growing. Silently, patiently, inexorably, they rise toward the sky, the roof of the world under construction, a project that began 50 million years ago and will continue for 50 million more, a demonstration of the creative power of natural forces, a testament to the dynamic nature of our planet, a gift to all who take the time to understand and appreciate them. The mountains are speaking, but in a language of stone and time, a language we are learning to read, a language that tells of collisions and compressions, of uplift and erosion, of the slow but certain transformation of seafloor into summit. Listen, and you can hear them. Watch, and you can see them changing. The silent growth of the Himalayas continues, and we are here to witness it, to study it, to marvel at it, to be transformed by our encounter with the highest peaks on Earth.